Yesterday we graphed exponential functions and we solved some exponential equations, but we just barely scratched the surface of logarithms. We got to talk about what a logarithm means. For example, if I say what is log base 5 of 1 over 25, think about that for a second. Log base 5 of 1 over 25. What do you automatically know about that answer? It's got to be negative, because how else can an exponent of 5 give you 1 over something? So it's definitely negative something. It's negative what? Negative 2, because 5 to the negative 2 equals 1 over 25. So you understand what logarithms mean. We graphed exponential functions. Here's where we left off last time, graphing logarithmic functions. Now, before I do the one on the handout, let's review the exponential function just for a second. If I gave you, I asked you to graph y equals, let's say, e to the x. Number one, you don't freak out when you see an e. You go, it's almost what? 3. It's almost 3. So it looks a whole lot like y equals 3 to the x. You can make a table for that if you needed to, but my goal is for you to not have to need to make a table for graphing exponential functions. The two things that I said I wanted you to know about any exponential function: if it hasn't been shifted left, right, up, or down, what's its critical point? 0, 1. 0, 1, because regardless of what the base is, anything to the 0 is 1. So 0, 1, and then does the exponential function have a horizontal asymptote or a vertical asymptote? Has a horizontal asymptote. Where is it? 0. At y equals 0, the x-axis, if the graph hasn't been shifted left, right, up, or down. So there's a horizontal asymptote at y equals 0. If you know the critical point, the horizontal asymptote, and the basic shape of the graph, then you can graph that exponential function very quickly without having to make a big XY chart. And that's the goal, because if you had to graph it on your calculator, you could. I just want you to have a quick mental image of what it looks like before you hit that graph button on your calculator. What's the inverse of e to the x? What function undoes e to the x? Natural log of x. And you know that when you graph a function and its inverse, the two graphs are reflections of each other along the line y equals x. All the ordered pairs are reversed. So if the exponential function goes through the critical point 0, 1, what's the logarithmic function going to go through? 1, 0. All right, here's the line y equals x. The line along which you could flip any graph and have the graph of its inverse. Here's the point 1, 0, which must be on the graph of the inverse of e to the x, which is natural log of x. And this graph should be the mirror image of that graph. I'm not real good at flipping things in my head, but I've done this just long enough that after I graph it, I can say, oh yeah, those two are mirror images of each other along that line. So if this is the graph of y equals e to the x, then this is the graph of y equals natural log of x, because those are inverses of each other. They're reflections along that line y equals x. All right, so what you need to have in your notes is that y equals natural log of x. The critical point is 1, 0, because the critical point of the exponential function is 0, 1. And what's the equation of the vertical asymptote? X equals 0. Y equals 0 is the horizontal asymptote for the exponential function. X equals 0, better known as the y-axis, is the vertical asymptote for the logarithmic function. So here's my graph of y equals natural log of x. What is the domain of that function? What is 0 included or not included? Not included. 0 is not included, but you can go forever to the right, so the domain is 0 to infinity, not including 0. Now, actually, that was in my definition up here. For all x's greater than 0, natural log of x is some number, means that if you raise e to that number, you get back the x that you started with. But we had the restriction right here. We were only going to take natural log of numbers that are greater than 0. That's because there's no power of e that's going to give you 0. There's no power of e that's going to give you a negative. Therefore, we can't take the natural log of 0 or negatives. We can only take natural log of positive numbers. So here's our basic graph of the natural log function. Really, log base anything looks like that as long as it hasn't been shifted left, right, up, or down. In number 68, how has that graph been shifted? How does that subtracting 2 before you take the log affect the graph? What we do before we apply the function, it doesn't matter what the function is, absolute value or square or cube root or whatever, what we add or subtract to or from x is our horizontal shift, and that horizontal shift always works the opposite of what we were expecting. So that graph is shifted 2 to the right. What does the 1 added on the end do to the graph? Move it up 1. So if we had said the usual critical point is 1, 0, what is it for this graph? If you put your pencil on 1, 0 and shifted it to the right 2 and up 1, it would be at the point 3, 1. And that's your critical point. You can double check it by letting x be 3. If you let x be 3, you have natural log of 1. What's natural log of 1? What's the exponent of e that gives you 1? 0, and then 0 plus 1 is that 1 right there. So the critical point is 3, 1. The vertical asymptote, which is normally at x equals 0, has been shifted where? 2 to the right would give you x equals 2. If your vertical asymptote is anything other than the y-axis, you have to dash it in to show me that you know there's a vertical asymptote there. Now, this may be the one I was thinking of yesterday when I said you have to dash in that vertical asymptote because the calculator doesn't do a good job of showing it. It can't show a vertical asymptote. I'm graphing y equals natural log of x minus 2 plus 1, and just on a standard graph. Ah, yes, that's the one I was thinking about yesterday. When I have people who don't know anything about logarithms and they just graph that on their calculator and copy down whatever they see, their graph stops right there. And if your graph stops right there, I know you fall into the category of don't really understand logarithms if you think it stops right there. The calculator just can't graph that vertical asymptote and show that that graph is getting closer and closer to it. So make sure that you show me you do know where that vertical asymptote is. Yes, so exciting. Number 74 said show that by graphing that f of x equals e to the x over 3 and g of x equals natural log of x cubed are inverses of each other. Anytime I ask you to show me a graph in the homework, you can just graph it on your calculator and then use what you know about the graph to make sure you're accurate. Your picture is accurate but then just transfer a reasonable facsimile of that onto your homework paper. If you did that on your TI 83 or 4, you would have y equals e to the x over 3. E is over your natural log button. X over 3 is one of your functions, and the other function is natural log of x cubed. Sure enough, it looks like the two graphs are reflections of each other. Actually, they kind of do that. Ooh, I did pretty good for freehand in there. Here's your line y equals x. You could even graph that on the calculator as a third function. And then do your best copy of that onto your homework. All right, what else do we need to be able to do with logarithmic functions? Well, there's something I need to show you on page 52 of the book. Logarithms are just a different way of writing exponents, right? If I give you exponential form, you can change it to logarithmic form. If I give you logarithmic form, you can change it to exponential form. So if logarithms are just a different way of writing exponents, then all of your exponent rules ought to still apply to logarithms. They look a little different, but all of your properties of logarithms come from your properties of exponents. You have a property of exponents that says when you multiply two expressions, what do you do with the exponents? You add them. You have a property of logarithms that says when you have two logarithms added together, you can write that as a single log by multiplying their arguments. That comes from the product rule of exponents. And then with exponents, you have a quotient rule that says when you divide two expressions with the same base, what do you do with the exponents? You subtract, so you have a property of logs that says the difference of two logs can be put back together as the log of a quotient. And then this third rule tells you if you have a log of something to a power, you can bring the power out front and multiply it times the log. That comes from the power rule of exponents. Those three properties allow us to take logs of big, horrific algebraic expressions and break them down into separate logs. That's going to be helpful when we're taking the derivative, whatever that means. If you give me the derivative of some huge, ugly rhinoceros, and I can break that rhinoceros down into parts and just take the derivative of each part, that will be easier. So we'll be taking logs apart because it makes taking the derivative easier. We often put logs back together so that we can solve equations. If we have log of something plus log of something plus log of something equals something, we can put that back together as a single logarithmic expression and then change it to exponential form. So the next things, well, let me see this note right here. Because e to the x and natural log of x are inverses of each other, they undo each other. Natural log of e to the x just gives you x. Natural log and e undo each other. Or e to the natural log of x is just x because the e and the natural log undo each other. That allows us to simplify number 82. What's the natural log of e to the 2x minus 1? 2x minus 1. I still don't know exactly what 2x minus 1 is because I don't know what x is. but I know that natural log and e undo each other and just leave me the exponent. Number 8, or 86, evaluate -8 plus e to the natural log of x cubed. How much can you simplify that for me? -8 plus x cubed, because e to the natural log undo each other. This did not give me any indication that I should factor. If I had to factor it, I could. But if there's nothing in the directions that tell me to factor that, I'm just going to leave the answer as either -8 plus x cubed or write it x cubed minus 8. Those two things mean the same thing. All right, what I just showed you in the book, I got a little bit ahead of myself. That was the properties of logarithms that we're going to use to do 94 through 106. 94 through 98 say use the properties of logarithms to expand the logarithmic expression, express powers as factors. Express powers as factors means use that property C when you can, or in this book it's property 3. When you can, express this power Z as a factor by bringing it out in front and multiplying it times natural log of x. So 94 through 98, and when we hit the calculus, we're going to be finding a derivative of something ugly like this. It'll be easier to find that derivative, whatever that means, if I write it as a sum or difference of logarithms. What could I do? What in the world can I even do to 94? You can write the cube root as the exponent 1/3. And then what? Bring the 1/3 out front. That is what is meant by the express powers as factors. If you have natural log of something to an exponent, you can bring the exponent out front and write that as a factor. And all the time that you've been doing that in Algebra 2, or we'll play like you did it in pre-calculus, this is what it has been leading up to, giving us an expression that's easier to find the derivative of. Now, I'm wondering about one other thing. Is that as far as I can go, or can I write that as 1/3 times natural log of z plus natural log of 1? In other words, can I distribute natural log? I only have a few people willing to commit to an answer on that. The rest of you are still thinking hard. Think about it this way. Logs are just a different way of writing exponents. Can you distribute an exponent through a sum? Oh, you know that. You can't distribute an exponent through a sum. You can't distribute a logarithm through a sum. So that is as much as we can do to number 94. What about 96? Take that apart. That's the log, the natural log of a product. How do those properties on page 52 tell us to take apart the log of a product? Will it be a sum, a difference, or a product? So it'll be a sum. That'll be natural log of z plus natural log of z minus 1 squared. Or if I want to go ahead and take care of that last exponent in the same step, I could have just brought it out in front of the natural log of z minus 1. Oops. And if I do, it's not still there. So whatever find the derivative means, trust me, it's going to be easier to find the derivative of this than it would be to find the derivative of that. Even though technically I could do either one, it's easier to differentiate that. All right, what about 98? Can you just say, well, the natural log and the e will undo each other and all that will be left is 1? Not quite. How could you write that e in such a way that you could say natural log and e just undo each other? What do you mean by distribute? Put it in both the numerator and denominator? Is that what you mean by distribute? Oh, okay, okay. You could use this property too that says log of a quotient can be written as the difference of 2 logs. Actually, that wasn't what I was thinking. I'm going to do what you said, Glenn, and then I'm going to do what I was thinking and show you you get the same answer either way. You said I can write the log of a quotient as the difference of 2 logs. And then how can I simplify that further? What's the natural log of 1? 0. And what's the natural log of e? If they undo each other, do they just leave you a little blank spot of air? Oh, there's a 1 there. There's a 1 there. So natural log of e to the first is 1, and 0 minus 1 is negative 1. So Glenn, that worked just fine. What I was thinking was I could write natural log of 1 over e as natural log of e to the what power? Negative 1. And then I could say natural log of e to the negative 1. Leaves me the negative 1. So I like it when there are 2 different ways you can think about something and get the same answer. You don't have to think like I do. Sometimes you'd be better off not to think like I do. All right. 104 and 106 say write the expression as a logarithm of a single quantity. In other words, put that back together as a single log. We're doing just the opposite, the reverse of what we did in 94 to 98. Thinking about going ahead and showing you the shortcut. Normally I do a couple problems before I show you the shortcut, but think about this for a second. Back when we first were reviewing exponents, if I gave you something ugly like, let's say, negative 5, x to the negative 2, y to the 4th, z to the negative 6th. When you first started dealing with negative exponents, you may have put in a middle step. You may have said, that's negative 5 over 1, because that's what negative 5 is, times 1 over x squared, because that's what x to the negative 2 is, times y to the 4th over 1, because that's what y to the 4th is, times 1 over z to the 6th, because that's what z to the negative 6 means. But very quickly, you got away from writing that middle step, and you went straight to saying any factors with a negative exponent are going to end up in the denominator, and any factors with a positive exponent are going to end up in the numerator, and you didn't have to write that anymore. Similarly, with logarithms, instead of saying any factor with a positive exponent is going to end up in the numerator, any factor with a negative exponent is going to end up in the denominator. When I look at number 4, I think any natural log that has a negative coefficient, its argument is going to end up in the denominator. Any natural log with a positive coefficient, its argument is going to end up in the numerator. All right, so when I put that back together as a single log, I'm ignoring the 2 for just a minute. A single log of a fraction, what's going to be in the numerator of that fraction? Maybe I do need to put in a middle step. Just the x, because it's the only natural log that has a positive coefficient. If we wrote it as an exponent, it'd be the only factor that had a positive exponent. So the x is going to end up in the numerator. What's going to be in the denominator? The arguments of the logs that had a negative coefficient came from the denominator. Now what about that 2? What is squared? Where do I put that square? That 2 is the coefficient of everything inside the brackets. So when I write that as a log, it still applies to the x and the x plus 1 and the x minus 1. And on a test, it would be absolutely fine to leave that. I suspect that in the back of the book, remember or means either one's okay. I expect that in the back of the book, they may write it as natural log of x squared over x plus 1 squared times x minus 1 squared. If you can figure out what's going in the numerator and what's going in the denominator without a middle step, it'll save you a lot of writing. So how about 106? If I write that as a single logarithm, log of a single fraction, what's going to go in the numerator? The x squared plus 1, because that log had a positive coefficient. What's going to go in the denominator? X plus 1, x minus 1. And where does that 3/2 go? It's the exponent of the whole fraction. I always want to simplify things as much as I can. That's just the rule I'm sticking with. If that argument would simplify, I would want to simplify it. Will it simplify? The only way it would is if I could factor the x squared plus 1. Can I factor the x squared plus 1? It's the sum of 2 squares. You could try, you could put some stuff down and play with it, but you'd never get it to work out to be x squared plus 1 unless you threw some i's in there, and you don't want to do that. So that's as far as I will simplify. All right, last problems. Holy cow! What are we going to do if we finish early?
Who's our homework?
Yes. I'd be okay. I'd be fair.
Watch the video.
We could watch my, oh, I forgot his name.
Burger.
This, is it? Have you already watched him?
No, I read it.
Oh, okay. I was going to say, isn't he a nerd? He's the most fabulous nerd. Let's see if we can solve these equations. 108 and 110, we're solving equations. And I didn't leave us very much room, so I'm hoping that there are equations that we can solve quickly. 108, the A part, solve e to the natural log of 2x equals 12. How can you simplify e to the natural log of 2x? It's just 2x. Because e and natural log undo each other. So 2x equals 12, which means x has to be 6. And you can check it by putting 6 back into the place of x. E to the natural log of 12 would be 12. When you're taking notes and when you're doing homework, make sure that your equations don't have more than two sides. I see folks write e to the natural log of 2x equals 12 equals 2x equals 6, and that makes no sense to a math person. I don't even know if that doesn't make any sense. So I will draw an arrow that says this equation transforms to this equivalent equation, but you'll never see me write an equation that has four sides. That doesn't make sense. All right, what about the B part? Can you squint really hard and tell me that answer without doing any work at all? I heard undefined. I think there's an answer. I think there's one thing that will make that true.
-0.
And what's -0 the same thing as?
0.
0. You know what? If you put -0 on the test, I'd give you credit for it. But it would have a smiley face or kind of cockeyed face beside it. If you need to write a step, you can say natural log of e undo each other and leave you -x equals 0. If you had to, you could show that you divide both sides by -1, but then I'm going to laugh at you. This is x equals 0. And it checks because natural log of e to the 0, what is e to the 0? 1. And what's natural log of 1? 0. Cool. All right. 110, the A part, natural log of x squared equals 8 might require a little bit more thinking because we don't have natural log and e undo each other. Any suggestions? Pull the 2 out? I certainly could. I'm not sure it would be helpful, but I could say 2 well, you know what? This would be okay. 2 natural log of x equals 8 is what you're suggesting, and that's okay. What would you do next? Divide both sides by 2 and say natural log of x equals 4, and then what? When you're stuck on a logarithmic equation, see if you can change it to an exponential equation. In exponential form, the base is what? E, and e to the 4th would have to equal x, and that's the answer. So that wasn't what I was thinking, but that's a perfectly good way to do that problem. What I was thinking was right here, I could say e to the 8th equals x squared. But something interesting is happening here that we're going to have to think about. When your brain says take the square root of both sides, what goes right along with that? Don't forget the plus or minus. So when we take the square root of both sides, we'll have x equals plus or minus e to the 4th. Notice I didn't take the square root of 8. I said, what do you multiply times itself to get e to the 8th? And that's e to the 4th. But would both of those answers work, or would only the positive e to the 4th work? Certainly the positive would work. If I put positive e to the 4th here and squared it, I'd have e to the 8th. Natural log of e to the 8th would be 8. What about the negative?
It doesn't matter.
Doesn't matter because
Because
it's
it's to an even power. It would be positive.
all right. Let me think about that.
No, because you have to square it in the 4th to the 2. You add them. No, I'm sorry, you multiply them. So it'd be x 8, so they could just.
What I'm trying to determine is whether or not negative e to the fourth is a solution. Let's agree on that. Would negative e to the fourth check? If I tried to check it, it would be natural log of negative e to the fourth squared, that's just putting negative e to the fourth in place of x, equals 8. Is that a true statement? What do you get when you square a negative? A positive. So that negative e to the fourth squared is e to the 8th. It's positive e to the 8th after I square it. Is that a true statement? Yeah. That is a true statement, which means that this solution or this equation actually has two solutions, both e to the fourth and negative e to the fourth, which is making me wonder, where should I have picked up on that right here? Right? If I solved it this way, I only got one solution, e to the fourth. If this was how I was going to solve the problem, how should I have known, oh, there's a negative in there somehow? By the way, that's a question I don't know the answer to. I'm not just faking here. I really have to maybe sit down and think about that, because it seemed like a legitimate way to solve the problem. Didn't do anything illegal. It just caused us to miss one of the answers. So let me think one more jiffy, and if I can't think of it right this second, then that's going to be my to think about this weekend. It's going to have to be my think about this weekend. There are two solutions, but I don't have off the top of my head a good explanation for why we should have known there was going to be another answer if we did the problem that way. So here's my note to myself. Think about that on the drive to Alabama tomorrow night. Because it's a 4-hour drive, I think I can figure it out in 4 hours. All right, one more. The B part. E to the negative 2x equals 5. Again, it's not like the previous problem where I had natural log of e undo each other. So what could I do?
Logarithmic.
If logarithmic form bugs you, you can change it to exponential form. If exponential form bugs you, or just doesn't seem helpful, you can change it to logarithmic form. What would that be in logarithmic form? Yes. Natural log of 5 equals negative 2x. You just want to check that that's right. By the way, that's marked out. If you want to check that that's right, then change it back to exponential form. Whenever I see natural log, I know the base is e. So this would be e to the negative 2x equals 5, and that's what we started with. So what's the only thing we have to do to solve for x? Divide by negative 2. Have you checked your answer enough in the back of the book to know that they're probably going to write negative 1/2? Natural log of 5. I would count negative natural log of 5 over 2 correct, no doubt. But I think in the back of the book, they'll probably write it like this. All right. I really like the idea of let's watch Mr. Berger together. Because you really couldn't get but 1 or 2 problems done on your homework. And hold on. The homework is finish what is at the bottom of the handout So finish this and read 2.1. Read chapter 1 review. Let me tell you about those problems at the bottom. When I give you practice test 1, it's going to have these same problems on it. These are the problems you need to make sure that you can do from the chapter 1 review. You're just getting a head start on studying for the test. If you want to go ahead and start working on those now, if you don't get them now, you will need to get them later. So let's look at this, and then you can mark that off your to-do list this weekend. Don't talk over my buddy here.
Calculus just gives us the answers to 2 basic questions. Okay, so what are basic questions? Well, I'm going to tell you right now. Now, to inspire the first question, I want to tell you something that actually happened to me yesterday. Trying to get in shape, so I went for a bike ride. Now, let me actually show you this. I went for this long bike ride. Oh, it was so long, but it nearly killed me. The bike ride, 30 miles long. 30 miles. 30 miles. Nearly killed me. And I have my bike. In fact, I started way up here. Here's my bike. I have this great mountain bike. Really pretty, by the way. And it actually is purple, in case you're wondering if I'm using the purple pen just to be colorful. But the truth is, I am using it to be colorful, and my bike is purple. In fact, it's a mountain bike, really fat tires. You can go anywhere on it. But I was going on the road. It's okay, I was going on the road. 30 miles. Did the whole trip in an hour and a half. Can you believe that? Well, I hope you can, because that's exactly what I did. Impressed? I was. Now, something interesting happened during this bike ride. Around 2/3 of the way through the bike ride, right around here, there was a road sign. And the road sign read 20 miles an hour. 20 miles an hour. And it turns out that that road sign was actually located 20 miles from where I started. So in fact, this distance right here is 20 miles. Right to there. Did I break the law? No. What does that mean? Did I break the law? Well, what I'm asking is, at the very instant, at the very moment that I crossed that road sign, was I going 20 miles an hour, or was I going above 20 miles an hour or below? So I need to find out here is the rate that I was going, the speed I was going right at that instant. Forget about all the stuff over here. You can go as fast as you want anywhere before or after, but just at that instant, the road sign says 20 miles an hour. Well, did I break the law? Well, that's actually the very first question of calculus. To find out instantaneous velocity. Velocity at any one instant in time. Let me actually try to enact this for you right now. In fact, I asked the crew, we don't know each other too well, you and I, but I'll just tell you a little bit about the behind the scenes thing. I asked the crew, I wanted to actually animate this because, you know, this is all sort of web, video, you know. So I wanted to actually animate and actually dramatically show, my goodness, I removed the 20 mile, you know, I removed the sign, by the way. Then you go as fast as you want. So much for the first question of calculus. Let's put that right back there. But what happened was, I actually wanted to do this for you live, okay? So I said to them, capture something that actually captures me on the bicycle and the ethos of me and my shape and everything. Well, they tried to do this, and look what they got. They got this little bear, and they said, well, you know, it's got you know, brown hair, and so that's the ethos, right? And a tricycle. My bike is not a tricycle, by the way, in case you're wondering. My bike is a real mountain bike. There it is. But okay, this is the little thing that they gave us. Okay, well, let me actually show this to you. And I want you to watch. And the thing to watch out for here, folks, is watch the velocity of the little bear, Professor Berger, at the very instant that he crosses this thing. Let's try this right now, shall we? This is going to be a live experiment here. So here I am starting right out of the screen. I kept going, that's how good shape I'm in, right? But at that very instant, you see it? There was some speed that I was traveling. At that very second I crossed the 20 mile an hour sign. How fast was I going? That is the very first question of calculus, finding instantaneous velocity. Okay, now let's just think about that for 1 second. And I want to actually sort of wonder, well, how can we even attempt to answer that? Well, I think that you actually have the ability to answer this question, at least to warm up to it. And actually, I want to pose it as a warm-up question. So what do we need to do here? Well, we know distance, we know rate, and we know time. So what I would like to do is get a relationship between distance, rate, and time. Anyway, distance does equal rate times time. And we're after the rate. So if I solve this for rate, I would see that rate actually equals distance divided by time. And you know what? This is, in some sense, the very heart of calculus. This is the heart of calculus. If you understand this basic formula, then you are well on your way to understanding calculus. And now you're saying, no, that can't be, because, gee, the calculus textbook is 5 inches thick and weighs 3 tons. Well, the calculus textbook is 5 inches thick, and this really is the heart of calculus. So great, we're making progress. Okay, now what's that second question? So the first question, finding instantaneous velocity. What's the second question? Well, the second question, actually, is something completely different. Completely different. This is going to be a geometrical question, and the question basically is, how do you find the areas of certain things? For example, you all know that if you want to find the area of a rectangle, that's actually not so hard. You just take base and multiply it by height. And you know, there are rectangles in life always occur. For example, you know, these bars that you eat to gain energy and stuff. These are great, by the way. These are really good energy. Oh geez, I've never eaten one of these actually. They're very chocolatey. Do you actually get energy from eating these things? I think you get or something. Anyway, well, before I ate it, you see, before I ate it, it was a whole rectangle. Now it's a much bigger. So you can find the area of those things. In fact, you can even find the area of slightly more exotic things. For example, you can find the areas of circles. For example, you might have, you know, CDs, right? You have CDs? No, but here's 2 CDs, right? And if you want to find the area of that, in fact, these are actually a little more interesting than just circles. They're sort of concentric circles. It's sort of a region and then there's a little hole inside there. But you can actually find the area of those because you might remember that the area of a circle is pi r squared. So those areas of disks, areas of uneven power bars, those are actually pretty easy to find. But what about more exotic areas? Suppose you want to find the area of, let's say, something really like an amoeba or something. Look at that thing. Now, I don't know a formula that gives you the area of that. I don't know a formula for that. Or suppose you want to find the area, cross-section area of an airplane wing. You ever saw an airplane? They're very pretty curves. If you ever take an airplane wing and chop it, well, actually, don't do that because then the plane won't be very good. But if you were to chop it off, you see it's very pretty. How do you find the area of exotic regions? Well, that's actually part of the second question. You can even ask a more general question. What about in 3 dimensions? Okay, for example, what if you wanted to find the area of something like this? Show you a 3-dimensional picture. Can you visualize that? That's a 3-dimensional picture. It's a donut. In fact, I happen to have one right here. You see, this is a donut. How would you find, not the area, how would you find the volume of this? How would you find the volume of a donut? Now, this, by the way, is a lot better than the energy bar. So if it comes down to eating an energy bar or a glazed donut, go for the donut. Okay, but I digress. Okay. So how do you find the volume of this donut? Or how can you find the volume of other funny shaped things? For example, you know, what can you find the volume of? Well, okay, thanks. You can find the volume of a football. Okay, how would you find it? There's no formula for that. So what would you need to find the volume of that? Well, the answer is you need calculus. So calculus actually will answer the question of how do you find areas of exotic shapes and volumes of exotic looking regions, like uneaten donuts or footballs. So that's the second question of calculus. Now remember, the first one was finding instantaneous velocity. And the second question is finding areas and volumes of really strange looking things. Completely different questions. Completely different questions. Well now, folks, I'm going to let you in on what I think is the most interesting secret and the most interesting fact about calculus of all. These 2 completely different questions turn out to have related answers. Isn't that incredible? Here we have 2 questions. One question is asking about how fast you're going at one particular instant. And the other question is asking about how do you find areas of really weird things? They're unrelated issues, and yet the answers link them together because, in fact, the answers are almost the same for both these questions. That, I think, is the really cool thing about calculus. The really cool thing. Okay, well, that's what calculus is all about. We're going to try to answer these 2 questions. And once we answer 2 questions, guess what? It's time for the final. Sorry. Okay, anyway, what we're going to do next is we're going to take a look at that first question again. We're going to take a look at me on the bicycle, and we're going to see if we can make some progress to figuring out how to find instantaneous velocity. Okay, I'll see you in a bit.